Okay, it looks like we're going. Let's start with the quick screen share. Okay, and so we're just doing a couple of quick conceptual questions to help you understand things here. All right. So imagine you got circuits, right? You could have a circuit here. There's an AC source, so some kind of function generator, and maybe there's a resistor, and maybe there's an inductor. Maybe there's a capacitor. Okay, so let's just do this random example to start. Okay, so in this case, um, okay, there's a bunch of words here up at the top. You could read that later. Let's focus on this. At very low frequencies, capacitors have enough time to become fully charged. When the capacitor is fully charged, how much current is going to flow near that capacitor?
None.
None. Okay, if no current is flowing, so if we're at low omega and basically no current, does it look like a break or a short?
Break.
A break. Okay, got it. Next, at very high frequencies, the capacitor doesn't have enough time to store any charge. Is it going to act like a short or a break?
Short.
A short. So what we have learned is if you take the function generator and drive it at low frequencies, the capacitor says no, no current allowed. It basically acts like an open switch or a break. Whereas if you're at very high frequencies on the function generator over here, this thing is going to act like a short circuit, like there's no capacitor there at all, and then no current would bother to go through the inductor. Okay, that's step one. So let's undo that one there. Okay, so next, let's look at the inductor now. We're talking about an inductor. It relates to the rate of change of current. So it relates to the rate of change. If you're at low omega, it's not changing very fast. Would we expect the inductor to have a large or a small voltage? If you have a very small omega, remember I is something like sine omega t, maybe minus a phase angle. But the idea is if omega is small, if it's a small number, and you take the derivative, the omega pops out. Is the voltage big or is it small?
Small.
Small. So take a guess. Is that going to look more like a short or a break? Just go with your gut. It's okay to be wrong.
Break.
It will look like a short. Breaks are like open switches and take up all. Let me give you an example here. That was a good idea. So this is not as intuitive, is it? Imagine you have an open switch. Right now, we could do KVL around this loop. There would be no voltage across the resistor. There'd be voltage E right here. The other voltage E would come across the switch. So it turns out open switches have large voltages. Closed switches, if we did the same circuit with the resistor, with a closed switch up there, there's basically no voltage across a bare wire. And so it turns out if you have a low voltage, that looks like a short. So I appreciate you giving that a shot. Did that make any sense? Or any questions about that? Okay. Now, if we put an inductor with a high frequency, take a guess. Is it going to be a break or a short?
A break.
A break. Okay, so the idea is this. Let's go to the next page and summarize this. So flip to the next page. This is the summary. There are 4 boxes we need to fill in. But basically, if you are trying to understand a circuit, anytime you have an inductor all by itself, at low frequencies, you could redraw it as a straight wire. At high frequencies, you could redraw the inductor as a open switch or a break. The opposite is true for capacitors. At low frequencies, the capacitor charges up and acts like a a break, whereas in this case, at high frequencies, it will act like a short because it doesn't have time. Okay. Now, resonance only makes sense if you have both L and C. So let's go look at those two cases. So this is where things get interesting. Suppose you have both of these here in series. At low frequencies, what do you think this combination would look like? Would it look like a short or a break?
Is it a break?
It's a break. Why? At low frequencies.
Capacitor breaks, so
Exactly.
break either way.
Exactly. Now, what about at high frequencies?
It's also a break.
Because what?
The inductor acts
Exactly.
like a break.
Exactly. So at low, this causes a break. At high, this causes a break. So it turns out at resonance, you get a short circuit. So this is why if you take an AC source and connect it to a resistor, a capacitor, and an inductor, at low frequencies, no current flows because of the capacitor. At high frequencies, no current flows because of the inductor. But when the porridge is just right, you do get current through the resistor. You're going to see that today. Now, just take a guess. What if you put these in parallel? If you put these in parallel, what would happen? At low frequencies, would it be? Go ahead.
Would be, I would think it would always be a short for both situations.
Exactly, except at resonance. At resonance, then it doesn't allow any current to flow because it's an oscillator and it resonates at the frequency you're trying to drive it through, and it will oppose any current flow. It's not perfect, but it turns out at resonance, if you have an LC in parallel, it blocks current. If you have an LC in series, it allows current to flow.
So I got a quick question.
Sure.
So what we're filtering then is the frequency?
What we're filtering is the amount of current that gets to a resistor in a circuit. Let me show you on the next page. Is that cool? So, so here's the idea, how you can understand these. So imagine we have our straight up circuit. Let's analyze this. So let's say we have our circuit. I know we've got our source and we've got our resistor in every circuit, okay? And so I'm just going to draw these, and you take the time to draw these with me, okay? So we'll fill in the shorts and breaks in a minute. Okay. And so let's do the capacitor here in red, and I'll do the inductor here in blue. So let's start at low frequencies. At low frequencies, what does the inductor look like? Remind me. Short or a break?
Short.
Short. What does the capacitor look like?
Break.
A break. So we'll just do that. How about at high omega? So at very large frequencies, at high omega, what do you think? How about the inductor? Let's start with the inductor.
The inductor is broken.
Broke. And what's the capacitor then?
It is a short.
And then, so what's going to happen at resonance?
Everything's shorting out, right?
Yeah, it's a short. So now let's think about this. Let's talk about the impedance here. So let's talk about the impedance. Remember, Z is a lot like resistance. It's basically a measure of how much current is blocked. Or how much you're impeding current here. So if you have an open circuit, is it going to be a large impedance or a small impedance?
Can you repeat the question?
Oh, sorry. Okay, so in this circuit here, the circuit for low omega, there's an open circuit. Is that going to be a large amount of impedance? Will it impede current flow a great deal? Or will it be a small amount of impedance? Will there be a large amount of current?
be really large.
It'd be large.
Yeah.
So let's just call it infinity. How about here?
Same thing.
Infinity plus 2.
Yeah. Okay, we'll do that. We'll carry the 2. Got it. All right. And then how about here? What's the impedance? Think of the impedance as the ohms in the circuit.
Didn't we say it was like 1 over R or something like that?
Careful. Z would be just R.
Okay.
If it helps, this is the equation we're going to use today. Z is equal to the square root of R squared plus XL minus XC quantity squared.
Did I
Oh,
see
minus.
somewhere yesterday though where we had like 1 over ohms?
I'll explain that in just a second.
Okay,
We're
okay.
almost there. Yeah. Sorry, that's supposed to be a minus sign there. Let me clean that up. So the idea was this. I don't know if you remember this. At resonance, the inductor and the capacitor happen to cancel out. And so all we get is Z equals R when we're at resonance. So resonance is defined by XL equals XC. So I'm going to write that down. XL is equal to XC at omega resonance. I'll write RES so you have it. So anyways, these two drop out at resonance. Anyways, so
What's
now
value of X? I'm assuming it's resistance.
XL is in ohms.
Okay.
And so is XC. So if it helps, just to remind you, XL is equal to omega times L. The more omega you have, the more ohms you get associated with the inductor. XC is the ohms related to the capacitor, and that's 1 over omega C. So we see that if you're at a low omega, a small omega gives you a large amount of ohms associated with XC. If you're at a low omega, you have a small amount of ohms with X sub L. So this is the same stuff that, is that helping?
Yeah, perfect. Thank you.
And now remember that these things are called reactances, not resistances, and Z is called impedance. That's fine. More on that in a minute. So, but they all have units of ohms. So X has units of ohms, Z has units of ohms. And at one special frequency, Z literally is the same thing as resistance. Okay, so now here's the idea. How do I get the current amplitude? I max is not current. It's the current amplitude, okay? It's the size of the wave. So it would be basically this is I max. The current amplitude is the height of the sine wave, okay? It's not the sine wave, it's the height of the sine wave. That is given by the voltage amplitude of the source divided by Z. It's not divided by R anymore because it's AC. It's divided by Z. So notice people kept asking me, what is that Z to the negative 1? Z to the negative 1 plot relates to current. So if you take the voltage of your source times Z to the negative 1, you get the current. The reason they didn't plot the current was because they just wanted to show you, they didn't want to have to rescale that graph all the time in that simulation. Questions about that? Or does that make sense what that Z to the negative 1 is now?
That makes sense, but I have it's probably a dumb question.
No, ask it. Go.
So for the second the circuit with the high frequency,
Yes.
when it says Z equals infinity plus 2, is the plus 2 just
Make
for
Eston happy.
comedy sense, or is there a reason for that?
Well, infinity plus 2 is infinity, and I figured, you know, we got to throw Eston a bone sometimes. That was all that was for.
Please keep it.
All right.
No, I totally get that, but I was asking if there was a reason why it's plus 2.
No, well, I'll tell you why, because Eston's not as cool as me, because I say plus 3, sucker.
Damn, dude, you gonna do that?
Yeah. Oh, let's do it. Let's do Aleph naught to the Aleph 1. There's your number theory for you. Do you guys know what that means? Do you speak Hebrew?
Nah, dude.
Well, what good are you then? So it turns out Aleph naught is the countably infinite numbers, and Aleph 1 is the uncountably infinite numbers. So anyways, yeah, so figure out what that is. Aleph naught raised to the Aleph 1. Stick that in your joint and smoke it. All right. That said, let's focus on this. Let's do one more thing here. Okay, how much current is going to flow in this particular circuit, the low omega circuit? If Z is infinity, look at this.
It's 0, no? Yeah, yeah,
Yes, exactly. No current flows, so that means the current amplitude is also 0. How about in this case? What's the current amplitude if Z is still infinity?
It's still 0.
Yep. And then what is the current amplitude in this case?
Yeah, just a V over R.
Exactly. And so in this case, Z happens to be R. So I'll call this, actually, I've been calling, I think, V max today. So let's do that. All right. Well, let's see what that looks like on a plot. So if we plot this, remember, we said Z was really big here. We said Z was really big here. And then at some level in the middle, at omega resonance, it dropped down to some level R, right? Okay. So is everybody cool with that? Does that make sense? So now let's go down to 31.14b. So now I want to look at the current amplitude. That one was a little bit different. It starts out low, it goes low at high omegas, and then at some special frequency, omega resonance, what is the peak value of current?
Is it V over R?
Yep. And this was that plot we saw yesterday that had Z to the -1 on it, right? Because isn't that proportional to I max? So, oh, whoops, I need to write something in there. Sorry. That plot of Z to the -1 was basically this. And this level here, was, I think we just said this was V max over R. What do you think about that? Could you guys handle that? I hope so. So going back to the quiz today, let's look at that last question now. The idea is I give you the actual circuit and I swept the frequency. So literally I changed the frequency and you can watch the current amplitude and try to figure out which one of these circuits I covered up. Yeah, so this is kind of fun. This is like mystery box. I don't want to spend the whole time watching this, but this was my favorite problem. Come on now, computer. Where is it? Oh, so there's what I did. I basically hid the circuit from you with this piece of PVC pipe. And so I showed you a resistor sitting here, and you have to figure out what the actual circuit is based off the performance of the oscilloscope. So it's only worth 1 point, but if you can get it done today, I think you would really have fun with that, and then you'd be done with lab. And so that's actually the filter circuit, so we don't need to cover that in lecture tomorrow.